Well, hello and welcome again to our journey into linear algebra. This is the second video in this section, and this section is on orthogonal transformations. So we looked at rotations before. I want to talk a little bit about a more general kind of orthogonal transformation, which is an isometry. So the rotation matrix above is an example of what we're going to call an isometry. An isometry is a transformation that preserves lengths and distances. When we rotate a point about the origin, its distance from the origin is unchanged, and hence if A is the matrix of the linear map, that preserves distances, then we can take a vector x multiplied by A, and the length of that resultant vector should be equal to the length of the vector I started with. And so we'll take this as our definition of an isometry. So suppose we have a little theorem here that suppose A is a real square real matrix, then A is an isometry, that is, it's a length preserving matrix or length preserving map, if and only if A is orthogonal, the matrix A is orthogonal. And worthwhile seeing a little proof of this. It's quite not very hard. So we need to recall this basic fact that the square of the length of a vector is the dot product of the vector with itself, and we can write the dot product as the transpose of the first multiplied by the second as matrices. So if A is a matrix representing an isometry, then this is true. So the length of AX is the length of x for all x. We can square both sides and then apply this formula up here. So squaring this one, we can, and then writing it using this, we can write this as AX transpose AX equals x transpose x. Remembering that the transpose of a product is the product of the transposes backwards, I can write this, and that's equal to that. And what I'm going to do now is I'm going to take this on the other side. I'm going to factor an x transpose out on the left and an x out on the right, and that's going to give me this fact, that x transpose A minus, I'll need an identity matrix here to make sense of it, times x is the zero vector. And this is supposed to be true for all x, for any x I like, and so I can choose my x to pick out each of the entries in this matrix, and they've all got to be 0, so that means this matrix in here has to be 0, and that means A transpose A is I, and that was our definition for A being orthogonal. The converse is much easier. If A is orthogonal, then we simply calculate the length of AX squared. So that's AX dotted with AX, and we can again write that using, as we did before, we can write this as AX all transpose AX, and expanding out the transpose gives us this. But of course A is orthogonal, so this is the identity, so that just gives me AX transpose X, which is X dot X, and that's the length of X squared, and then taking the square root across here gives us the fact that A is an isometry. Well as rotation matrices that preserve length, reflection matrices do the same thing, in fact, and so I thought we might find the form of a general reflection matrix that reflects about some line. This again is all happening in 2 dimensions. So we take T to be the linear map that reflects a vector B in R squared about some line y equals x. And we're going to use the idea of a change of basis argument, which you will have seen, I hope, in an earlier course in linear algebra, to find a matrix representation A for this linear map T. So here are the details of this. So here's the picture that we're looking at. So there's our line, y equals mx. And we're going to take in general a vector x, and we're just going to reflect it across the line. So this linear map is going to take any vector in R2 and reflect it across the line. And we'd like a formula for this. Now to do that, we're going to get we'd like to find a nice simple basis with respect to which we can write down the matrix, and then we can change basis back to the standard basis. So I'm going to take a vector 1m which lies on the line. It's not a unit vector, but just any vector 1m. So I put x as 1, and then from this y is m. That's going to be a vector that lies on the line. I'll call that vector a. Now, of course, if you apply this linear map t to this vector, it doesn't move because it's on the line. So it's not going to move anywhere when you reflect about the line. So t of 1m is equal to 1m. Now I'd like to get, I want a nice basis, so I'm going to take a vector perpendicular to this one, and that's fairly easy. I can just take minus m1 so that the dot product of these two is 0. So this vector is perpendicular to this one, and indeed perpendicular to the line. So when I reflect this in the line, it's just going to go over here. It's just going to go to minus itself. So I take b to be the vector minus m1 perpendicular to the line, and then when I reflect it about the line y equals mx, it just goes to minus itself, which is m minus 1. Now that means these two vectors a and b form a basis for R2, and so I can write down the matrix representation for this linear map with respect to this basis. So when I map 1m, it goes to 1m. So the coordinates of this with respect to the basis AB is going to be 1, 0. You get one of these and 0 of those. On the other hand, if I want the coordinates of this with respect to the basis AB, well, I want none of those, so it's got coordinates 0, and then I want minus one of these, so it's got coordinates 0, minus 1. So we can then write down the matrix for this P, the matrix P for this linear transformation with respect to this basis. And that's going to be 1, 0, because A goes to A. We need one of those, none of those. B goes to minus B, so we have none of those and minus one of those, and there's my second column. Now, of course, what we want to do is we'd like the matrix with respect to the standard basis, E1, E2, and we do that by using change of basis, using a commutative diagram. So we imagine that we have two copies of R squared here. This one, we've got basis AB both sides, and we've got a matrix representation, which is our P, with respect to these two bases. What we want is we want the matrix A with respect to the standard bases. And so as usual, what we do is, instead of going across here, we take an identity map here and an identity map here, so that's not doing anything. And we go down here, across there, and back up there. So we need to know what's the linear transformations that are sending me from one basis to the other. So call this one here Q, and Q is easy to write down because this is going from this basis into the standard basis. And so A gets mapped to itself under the identity. Its coordinates are 1 and m with respect to this basis. And B again gets mapped to itself, and its coordinates were minus m1 with respect to this basis. So there's our matrix Q. This is doing exact opposite, so this is the inverse of this matrix. And finally, the matrix A that we want, what do? We firstly take a vector and hit it with Q inverse, which is what I've written down here. We hit it with Q inverse. Then we hit it with P, and then we hit it with Q. And so our A will be QP, Q inverse, and I've just written those down. That's the inverse of my Q here, and multiplying it all out gives me this matrix here. So this is the matrix that reflects a vector in the line y equals mx. And you can easily check this, putting m to be 0, special case, so it's reflecting about the x-axis. You can put m is equal to 1, so you can see what it's doing about the line y equals x. and so on, and you can check that it all works and makes sense. So that's the representation for the reflection matrix, and that these are the two basic isometries in R2. And notice then that this matrix has determinant -1, and if you square this you get the identity, which makes sense. We know that every orthogonal matrix has determinant +or-1. If it's +1, we've seen it's a rotation. If it's got determinant -1, then it's going to be a reflection. And obviously, if you reflect something twice in the same line, you get back to where you start from. So a squared is equal to I. So just to finish this off then, now the product of two orthogonal matrices is easy to show as orthogonal. So we can multiply two orthogonal matrices, one with determinant 1, one with determinant -1, to obtain an orthogonal matrix of determinant -1. And this then represents a rotation and a reflection. So we can conclude that in R squared, an orthogonal matrix represents either a rotation if its determinant is 1, and if the determinant is -1, it's going to be a reflection, but then followed by some sort of rotation. And that's the complete story of these isometries in R squared. And in the next video we'll have a look at what happens when we try and lift this up into R cubed.